PowerPoint to recap some points from last week and help you prepare for this week's teaching session. Firstly, I want to just recap some essentials in research. In research, we have two variables, the independent variable, what you are testing and controlling, and the dependent variable, which is what you measure as a result of controlling the independent variable. Last week, we had scenario A, which compared patient satisfaction with their ear moulds between two manufacturers, Venus and Zeus. Audiologist Aker measured patient satisfaction in the two groups and compared these to see if they differ. In this instance, what is the independent variable and dependent variable in scenario A? Take a moment to think about this. Hopefully, you concluded that the independent variable was the ear mould manufacturer, and the dependent variable was patient satisfaction. That's what we were measuring. Sometimes it's helpful to remember the dependent variable depends or relies on the independent variable. In this case, satisfaction must be the dependent variable, as we expect it might change in relation to ear mould manufacturer. So why does this matter? In SPSS, the independent variable is typically the group. In contrast, the dependent variable is what we move to the test variable, dependent variable, or the test field section, and that will depend on exactly which test you're running. By knowing which type of data is your independent versus dependent variable, this will make it easier for you to determine which set of data you should place in the analysis options. My top tip based on last week's session is to make a plan before you perform any statistical tests. Remember, before you look at any graphs, descriptives, or perform any statistical tests, you should be confident that you know A, what the independent and dependent variables are, and B, how your data is set up / how you have input the data. Here is a video to help show you how I did this for the ear mould example. Data from last week's example. There are a few things I just want to point out that I hope will make it easier for you to interpret any future data sets. The first column here relates to the participant identifier, or their ID. It's common practice amongst research that every single person who takes part is given an anonymous code which relates to all of their data. This is particularly important for instances where you would like to either remove a case because it's an outlier, or to go back and interpret why one particular patient might be skewing data. None of the examples we look at worry about the participant ID, but it's important for you to know that's what it means. The second column here relates to the ear mould manufacturer, and you can see that we've got some 15 that have a number 1 and 15 that have a number 2. But what does that actually relate to? To find that out, you need to go to something called the variable view at the bottom here. Each row represents one of the variables in the data. So the first one is their ID, and that's a nominal scale. It's a name I've given to each participant uniquely. The second is the manufacturer. And if you move along to this values section, you'll see that I've told SPSS that a score or value of 1 means that the participant trialled their ear moulds from Venus, and that a score of 2 means that they trialled their ear mould from Zeus. Looking back to the data, we have this option here called a value label. If I highlight the manufacturer column and you watch this column whilst I select this, you'll see that what happens is that SPSS, when correctly coded, will swap between the numerical number I've given the group and the label, in this case the manufacturer's name. Finally, we've also got the satisfaction score, and critically I've coded that to tell SPSS that that's a scale measure. That's really important. If you don't allocate the name correctly to this measure value here, SPSS will give you some warning functions. So, how do we know that the satisfaction is a scale? Well, in this case, our satisfaction score is the dependent variable. That's what we're measuring as a result of the independent variable, the manufacturer. Remember, it's the manufacturer we are changing, and we are measuring satisfaction as a result. Perfect. So, in summary, there are steps you should go through to explore the data. So first of all, to look at how the data has been set up, or if you're typing it in for the first time, typing it in a way that SPSS can recognise. Secondly, you should produce a histogram of the data with the normal distribution curve overlaid, and that's to start checking for whether your data appears normally distributed. In addition, you should use the Explore option to gather descriptive statistics and check for normality, and that includes having to manually calculate whether the skewness and kurtosis values are significant. Once you've done those steps, you need to make a judgment on if your data is normally distributed. If it is normally distributed, then you should select the most appropriate parametric test for your data, for example, the independent t-test. If it's not normally distributed, then select the most appropriate non-parametric test, which we'll cover this week. Last week, we ran out of time to cover another form of parametric testing, called analysis of variance, or ANOVA for short. We use ANOVA for any scenario that we have two or more independent variables, for example, more than two groups. With t-tests, we can only compare two groups at a time. We could run multiple t-tests to compare each group to each other, but that risks inflating a type 1 error. Instead, we use the ANOVA to compare two or more groups, but rather than compare the mean, we compare the variance in groups. So here is a scenario that requires the use of an ANOVA. So in this example, audiologist Bill has access to a huge questionnaire dataset from patients who have completed a questionnaire called the Hearing Aid Handicap Inventory for the Elderly. Bill has followed these groups of patients for several years, and he's grouped them into the following. Group 1, people who've never owned a hearing aid. Group 2, people who've tried a hearing aid in the past but now don't wear one. And Group 3, people who are currently wearing and using their hearing aids. Bill wants to know whether hearing aid experience will cause difference in their latest overall or global HHIE scores. Our null hypothesis is that there will be no group difference in the scores across the three groups. In contrast, the alternative hypothesis is that the HHIE scores will be lowest, and that represents a better score, for Group 3, as the use of hearing aids has improved their participation in life. At this point, Bill isn't sure how Groups 1 and 2 might differ, if at all. Like the t-test, we can have a look at analysing this data, and I'll show you a video now of how we might go about doing that. Our data is normally distributed, we can now go on to perform the one-way ANOVA. Before we do that, do just make sure that the data hasn't been split, so just go to Data and make sure that Analyse All Cases Do Not Create Groups is selected, and we can see that because we get a warning to say that the split file function is off, which is what we want here. So to actually run the one-way ANOVA, go to Analyse, select Compare Means, and then across at the bottom there we're looking to select one-way ANOVA. We want to take the HHIE score and move it to our dependent list, and then we're looking to compare the groups, so that becomes our factor. We're not going to specify any contrasts here, but we do want to specify some post hoc tests just in case we're looking at any significant differences between these groups. Now, there are lots of post hoc test options. I'm just going to select Bonferroni as one option. Do have a look at Andy Field's textbook. There's a whole section just covered on post hoc tests. There are various pros and cons of each one. In this case, Bonferroni more than suffices for what we need, and the significance level is correct. Please also have a look at the options. My personal preference is for SPSS to give me the descriptive statistics at the same time as the ANOVA. That's my personal preference just because it means your mean and all the other essential descriptive statistics are just above your ANOVA. So when you get your ANOVA results, you don't need to scroll all the way up to where you've previously got your descriptive statistics. They're there right next to the ANOVA output. A bit like our t-test, it's also good to have a test of the homogeneity of variance, and so select that here and we'll come to that in just a moment. We don't need to worry about the others just at this point in time. So once we're happy with that, if you select OK, that will automatically run the ANOVA. So the first thing we get is the descriptive box, and I've selected this, and as I've said, it gives us an overview of the data, such as the mean, standard deviation, etc., for each of the groups. We've then got the homogeneity of variances box, and again, this is the Levene's test that we saw for the t-test. Effectively, what we're interested in is to see whether the significance value is less than 0.05. In this case, it's not, it's above that, so we can be rest assured that this data between groups is normally distributed, and we can correctly go on to interpret the ANOVA. So moving down to the actual ANOVA, these are the results itself. So the first line here gives us some values between groups, and we can see that the significance is 0.0000, so effectively less than 0.01 even. So in this case, our ANOVA is flagging that there is a statistically significant difference between groups. However, at this point in time, we don't know which of the groups differ. Remember, we have three: those that have never owned a hearing aid, those that have previously trialled but are not currently using a hearing aid, and those currently using it. And it could be any one of those three, or two that differ to the other, or vice versa. The way we're going to tell which groups are causing this difference is via the post hoc tests. And remember, I selected Bonferroni. This is just one example. So what the post hoc tests have is it takes a group and then compares it to another group, and it does that per row. So the first section here is taking group 1 and comparing it to 2, and we can see that there is no statistically significant difference between those that have never owned a hearing aid and have trialled but aren't currently wearing one. When you compare group 1 to 3, so those never versus currently using a hearing aid, we can see that there is a statistically significant difference. Going back to our means, we can see that the difference is likely because those currently using their hearing aids have a much lower HHIE perceived disability on average compared to those never owning a hearing aid, and that's a positive direction. Secondly, the ANOVA post hoc test compares group 2 to group 1, so that's a repeat of the statistic here, and it confirms they're not statistically significantly different, and then it compares group 2 to group 3, and if we look across, we can see that there is a statistically significant difference between the two groups. Again, because the mean for those who have previously trialled and don't use a hearing aid compared to those currently using their hearing aid is very different, with those currently using their hearing aid having a lower and better HHIE score. The final row is a repeat of the above, so it compares group 3 with 1 and 2, and it reconfirms that there is a statistically significant difference between those two groups. Based on this, we're able to conclude that using a hearing aid for this group of people significantly lowers their HHIE perceived disability, so their overall HHIE score, relative to those who have never owned or have previously trialled a hearing aid. Perfect. So like with the t-test, we can also report an effect size for an ANOVA. Remember that a significant effect just proves that there was a difference between groups, whereas an effect size helps us to quantify how big that difference is. For ANOVA, we use something called omega squared, denoted by this Greek symbol, and like before, Cohen has defined the levels that are small, medium and large as shown on the screen here. The equation for working out the effect size for an ANOVA is shown here, and your worksheets run through that. So I've worked out the effect size for our ANOVA, and we can see that it's a large effect size here. When we report our ANOVA, we must report the main findings. So that was that there was a significant effect of hearing aid ownership on global HHIE scores, and our post hoc, in particular naming which post hoc test we ran. So what are the clinical implications of this? Well, we know that based on our ANOVA, audiologist Bill can be confident that owning a hearing aid lowers HHIE score. He can also be confident that non-hearing aid ownership results in greater HHIE scores. He could use this evidence to counsel prospective hearing aid patients that hearing aid ownership can lower perceived hearing disability. He could also counsel them that owning a hearing aid does not remove all the difficulties. Instead, he can suggest where assistive listening devices might benefit patients. As an additional note, there are some other forms of ANOVA. There's the analysis of covariance, which is similar to ANOVA, but it indicates something called a covariate. This is just another factor which might be a potential source of error. There are also some factorial ANOVAs, which I'm not going to go through, but you should be aware of in case they're relevant in next year's project. So let's go to our worksheet example. So in scenario C, Shaq compared two groups who took ginkgo biloba, and that's a health supplement, with a placebo group. He measured tinnitus severity using the Tinnitus Functional Index, which is a questionnaire which asks people to self-rate how their tinnitus is impacting their daily life. In this instance, our independent variable is the group. It's whether they receive the placebo or the low or high strength ginkgo biloba. Our dependent variable is their score on the Tinnitus Functional Index. Your ANOVA should reflect the above. I'm not going to run through it as that's for your independent learning. However, use the previous example and that from week 8's module and the worksheet to help you run through this. I just want to remind you all about your assignment. For every example, you should include the descriptive statistics, in particular the ones that are relevant for your example. So for normally distributed data, that will be the mean, standard deviation, standard error and range. And for non-normally distributed data, which we'll cover this week, that will mean the median, standard error, minimum and maximum, and interquartile range. And I'll show you how to get these in this week's session. You should also include the results for normality testing, the skewness and kurtosis values that you computed, alongside the graphs, so the histogram. You should make a comment on what it looks like. For example, does it appear to follow normal distribution or not? And then the relevant PP or QQ plots. Again, make a comment on what this looks like. Because there are lots of graphs, you could choose to use this or include this in the appendix, but do make a comment in the text as to whether you think they look normal. And lastly, you should include the result of the KS and SW test result and your interpretation. So is it significant or not? and how you've used this to justify which statistical tests you're going to run. Finally, you should include the results of your SPSS output. You should also write a summary of 1, 2, or 3 sentences detailing the results of the test and also what this means. So in our ANOVA example, we included the results of the analysis, but also made a comment as to what it might mean for Bill. And that's exactly what we're looking for you to demonstrate here.